Alright, so I wanted to make a little video since it seems we're going to have a snow day today. And this should keep us on track. Just want to talk a little bit more about sequences, try to wrap things up here today. So first of all, one remark I should make is that I've used the term least upper bound or greatest lower bound. An alternative notation or terminology is sometimes sup, as in what's up. No, it's supremum, or this is infimum. So I have a couple homework problems that use this terminology. But you should recognize it's really the same idea as this and that. Should also mention that example 5 on page 536 is more or less what I wanted to do yesterday. So that's a nice example. That one actually has a differentiation that works out not too bad. Here, I'll take a second to do it. It's a sub n equals to n to the 1 over n, and you're supposed to show it decreases for n greater than or equal to 3. And what they do there, all right, is something which I was trying to show you guys last time, but kind of just didn't work out too nicely, is to look at the function f of x, which corresponds to this, the continuous extension, which would be x to the 1 over x. And then he does something really sneaky here. He converts that to exponential of the natural log of that thing, all right, which then, of course, is exponential of 1 over x, natural log of x, which, of course, then you can differentiate. And so you differentiate that. You've got exponential of 1 over x ln of x, of course, times d dx of ln x over x, right, by the chain rule. And, of course, the first thing is, again, just x to the 1 over x again. But this here is minus, how's it go? Minus 1 over x squared from the derivative of the log. And then, of course, minus log of x over x squared. So that's like the product rule or the quotient rule, however you want to look at it. In any event, you can see that df dx is equal to, we got here, x to the 1 over x times, I think I made a sign error. Oh yeah, there's no minus on the first one, that's a plus. Times 1 minus the natural log of x over x squared. Okay, so you know what log x looks like, right? It's got this kind of deal. That is actually, that's at 1, right? Natural log of 1 equal to 0, but out here somewhere at e, you get to natural log of e is equal to 1, right? So if you're out here, then you have natural log of x is greater than 1 for x greater than e. So certainly if x is greater than e, right? For example, if x was greater than 3, then that should do it. Oops, sorry, I'm getting off the screen here. If x is greater than 3, then that'll do it, because that will make this, what? That'll make f prime of x less than 0 by that formula right there. And so that implies that n to the 1 over n decreases for n greater than or equal to 3. I just thought that was a nice example because it's not too hard, the differentiation, but perhaps not too easy either. So nice example. I'm going to move on. So let me find a different cover sheet. So another application of the least upper bound I probably should have mentioned, but I neglected to, is just that we could use it to, give a careful meaning to repeating decimals, right? So like 0.3333 repeating, we could take as the least upper bound of this sequence, 0.3, 0.33, 0.333, and so forth, right? And in fact, if you look at page 539 in example 3, he actually proves from the epsilon n definition of a limit that the limit of this sequence is in fact 1/3. So I think that was a nice example. I'm not actually going to go through that one here. I should also mention that number 58 on page 547 actually has the inequality that I was just starting to search for last class, but we couldn't quite find. We proved that the limit as n goes to infinity of 2 to the n over n factorial was 0 by appealing to the bounded monotonic sequence theorem. But you could also argue directly by a squeeze theorem argument if you could prove this estimate, that 2 to the n over n factorial is less than or equal to 4 over n. Now, perhaps that's not obvious. We can talk about that another day, why that's true. Okay, I'll talk to you guys about that in person. But I thought I should mention that that's another way we could approach that problem. Okay. So, one of the topics we haven't touched on yet in class, and maybe you haven't seen before, is mathematical induction. There are some problems in this part of the material which are really attuned to the technique of mathematical induction. So let's talk about what that looks like. The property of mathematical induction, proof by mathematical induction, the way it works is as follows. You find some claim, which I'm going to call P of n, which is allegedly true for all natural numbers n. And the way to do mathematical induction is you prove the claim is true for 1. All right, that's the base step. And then you assume that the claim is true for n, for like an arbitrary n. And then you give arguments to show that n plus 1 holds true. Now, because you did it for an arbitrary n, and you showed that the next step of n plus 1 held true, then proof by mathematical induction says, you know what, that means that it's true for all positive integers. So here's the claim, number 57, from I think it was 11.2 in the handout. It says that if we define this sequence recursively, a1 being 1 and a sub n plus 1 being twice the previous 1 plus 1, then it follows that the formula for this guy is 2 to the n minus 1. All right? So here is the proof. Base case, n equals to 1. So I look at, is this formula true for n equals to 1? Well, yeah, sure enough it is. Great. Then the next step is I assume that it's true for n. I assume that an is equal to 2n to minus 1. Now, next I want to give evidence that it's true for n plus 1. So I consider n plus 1, a sub n plus 1 is, well, it's 2a to the n plus 1. This is the definition that was given to me, the recursive definition of the sequence. Great. Then going from here to here, I use the induction hypothesis. So the induction hypothesis is this. This is right here is the induction hypothesis. And right in this step right here, I used it right there to change that an to that. All right. Now once I do that, algebra takes over, and I distribute the 2 and use laws of exponents. 2 times 2 to the n is 2 to the n plus 1. Minus 2 plus 1, of course, that's 2 to the n plus 1. But hey, check it out. Lo and behold, I've just shown that the claim is true for n plus 1, because a to the n plus 1, a sub n plus 1 is 2 to the n plus 1 minus 1, which is the alleged pattern which holds for the nth term. And so therefore, Pn implies Pn plus 1. Therefore, Pn is true for all n of the natural numbers by proof by mathematical induction. So maybe you haven't seen this formal style of argument before, but it's something that I think every person who takes calculus ought to be exposed to, whether or not you are. It's a question of the instructor whether or not they want to do it. But I think it's worth a minute or two of our time. Here's another one. Number 60, we're given a1 is 1, an plus 1 is equal to an minus the 1 over n times n plus 1. We're supposed to prove that this implies that the formula for an is 1 over n. I mean, when I look at that, that's not at all obvious, but here's the proof by mathematical induction, which is pretty easy. First of all, if we plug in 1, 1 over 1 is 1, so it checks the base case is true, a equals 1 is true. Next, I suppose that the claim is true for n, an is 1 over n, and I consider an plus 1. Now an plus 1 here is an minus 1 over n plus 1 times n, and then I use the induction hypothesis, which I'll underline again. This is the induction hypothesis, right? I'm using that induction hypothesis right there, okay? And usually I'd write this out in words, but you know, just trying to not be too wordy here at the moment. Anyway, so that's that minus that. I do algebra, I can factor out the 1 over n, and then make a common denominator here, and the minus 1's cancel. Leaves us n over n plus 1, but then that n cancels with that n, and it leaves me 1 over n plus 1, which is what we set out to prove. an plus 1 is equal to 1 over n plus 1. So we've shown that this being true for n implies that this is true for n plus 1, which means by proof by mathematical induction, it's true for all n. Okay, so great. Maybe you've seen it before, maybe you haven't, but that's how mathematical induction goes. Sometimes it's a useful method of argument. I thought it would be healthy for us to also look at a couple of recursive examples. So these are taken from the homework. I thought it would be good for us to just kind of sort through these right quick. Number 47. So the instructions are to look at the recursively defined sequence and see if you can find the formula for it after writing out the first like 6 terms or something. So they told us a1 is 1, and then they told us that an plus 1 is defined to be 1/2 of an plus 1. And okay, so I try it out. A sub 2, 1/2 of a1 plus 1, which is 1/2 of 1 plus 1, which is 2 over 2, which is 1. Oh, okay, great. A sub 3, well, 1/2 of a sub 2 plus 1, which is 1/2 of, hey. So it's like, do I really need to do 6 of these? I think I see what's happening. Apparently, this is a really annoying way of defining the constant sequence 1 in a recursive fashion, all right? So a sub n is equal to 1 for all n in the natural numbers. There you go. That's the formula for this recursively defined sequence. Now sometimes it takes a little bit more work to see it. Here's the next one. Let me try to scooch this up a bit here. Get out of here. Get out of here. All right. So the next one was number 52. I picked that one. A1 is 1. An plus 1 was 2an plus 1. So just to emphasize here, you know, this was what was above the green line is what was given here. Okay. So like that was the given problem, and then like find the formula for an. We found it was 1, and in this one we're given, you know, that's the recursive definition of the sequence, and we're supposed to figure out what the formula is for it. So I did the legwork here, the grunt work, if you will, plugged in the numbers and saw what happened, and I looked at it, and it didn't pop right out at me. Like, I was a little bit worried for a second. I was like, what? What's the pattern here? You know, I can't see. What is the pattern? 3, 7, 15, 31, 63, 127, 255. So, I mean, then you just got to have some insight, all right? You got to have some kind of number sense and go, wait a minute, that's 2 to the n minus 1, right? Because this is 2 minus 1, this is 4 minus 1, 8 minus 1, 16 minus 1, 32 minus 1, 64 minus 1, 128 minus 1, 256 minus 1. And of course that, you know, 8 is 2 to the 3rd, 16 is 2 to the 4th, 2 to the 5th minus 1. And so you can see that that is in fact the pattern. But it did take a moment of inspiration. And I'll be honest, folks, I mean, when you're trying to find the formula for a sequence, that moment of inspiration may or may not come to you. You just, you know, you got to do your best and try to see if you can see a pattern. There's no algorithm. I mean, this is much like parametrizing a curve or something. It's more of an art than it is a procedure, all right? But certainly getting your, you know, like I said, doing the grunt work, crunching some numbers is the first and you know, important step to take there. So I've asked you for some epsilon n proofs, quote unquote, in the what's the word? The homework. So I thought I should share a few. There's also some nice ones given on page 538 and 539 of the handout. Excuse me. Here's one. So suppose we want to prove carefully with an epsilon, with an epsilon n argument, type argument, that the limit as n goes to infinity of n squared is infinity. So what I have to do to prove this is to pick an arbitrary positive number, in this case m, all right? And then I want to choose some natural number n such that whenever I take things past that natural number, it forces the value of the sequence n squared to be greater than my given m. So I thought about it for a second, and I realized, oh, I should make my n. Sorry, the other one seems to have lost its feet. Just try to make my big n's look different than my other things. Anyway, there it is. So if I choose big N to be some natural number larger than the square root of m, certainly that's something you can do, right? I mean, if you take a positive number, you take the square root, it's another positive number. So continue down the number line, you're going to get to another positive whole number, sometime. So there I pick one of those. And then if I pick n larger than that n, it's of course then larger than the square root of m. But then if I square this inequality, it's positive inequality, so I can square it. That gives me n squared is greater than m, which is what I need. That says that the nth term in the sequence is larger than m. M was an arbitrary positive number. That proves from the definition, actually, that the sequence n squared goes to infinity as n goes to infinity. So, not especially exciting, but there's an example of the kind. I think I've asked you one like that in the notes. It's not much harder than that. Another example of this kind of proof, epsilon n proof. This one's actually an honest to goodness epsilon. This is a convergent proof. So this is I'm proving that the limit as n goes to infinity of e to the minus n is equal to 0 directly from the definition of the limit. All right. So here's the way that goes. We let epsilon be greater than 0, and I'm going to choose n to be. I'm going to choose a natural number n, which is greater than natural log of 1 over epsilon. All right. Now the reason I did that was because I know that if I do that, it makes this happen down here. Okay, I did some scratch work on the side to figure that out. Let me go grab my scratch work. I'll show it to you. Here, it's very exciting. So I was like, what I need is that epsilon e to the minus n is less than epsilon. So if that means minus n is less than the log of, because the log is an increasing function, so I can take the log of that. That's positive, so that's equal to e to the minus n. So I take the log of the inequality, which I can do because log is an increasing function, and then I, oh shnikes. Oh well. See, my scratch work it was a little bit scratchy. Because if I bring minus over there, I should really switch that inequality around, shouldn't I? But I think I didn't make a mistake nonetheless, because, well, over here, look, it works. So I picked n to be, because I got n greater. I want to pick this n natural number greater than the log of 1 over epsilon. Keep in mind here, epsilon is arbitrary, small. You think of it as small, but it's a small positive number. So certainly I can take the log of 1 over that. So yeah, definitely such an n exists, all right? And if we suppose that little n is bigger than that n, all right, that would mean that little n is also larger than the log of 1 over epsilon. But I can take the exponential of this inequality. Why can I do that? Because the exponential is an increasing function, so it preserves inequalities. Like e to the n is greater than e to the log of 1 over epsilon. But of course that simplifies to 1 over epsilon. And then if I have the e to the n is less than 1 over epsilon, that implies that epsilon is greater than 1 over e to the n. But of course 1 over e to the n is e to the minus n, right? Consequently, I've shown that the absolute value of e to the minus n minus 0 is less than epsilon, which, going back to the definition of limit, proves that e to the minus n goes to 0 as n goes to infinity. Now, if you had calculus 131 here, you should have done some epsilon delta proofs in your course, and so this is not entirely bizarre. If you didn't, this may be like completely new thinking, and that's okay. We'll get through it. I've assigned you a couple of this in the homework. It's not, it's a relatively small part of what's going on the next test, but it is something I'd like you to try to understand. So I'll move on here. We can talk about more of them in class if you've got questions. So up next here is the properties. I just decided to collect all of our limit laws, if you will, for sequences together here in one big list. All right, and so here they are. Get this centered here. There we go. So if we have two sequences, an and bn, which converge to a and b respectively, as n goes to infinity, all right, then what does that tell us? Well, that tells us that the sum of the sequences converges to the sum of the limits, just like you'd expect. A constant times a sequence converges to the obvious thing. A product of sequences converges to the obvious thing. These, just to take a second here, this what does this look like? In the other notation, this looks like the limit as n goes to infinity of an bn equals to the limit. Now this step I'm making, this is only legit if the limits I'm writing here on the right hand side are in fact existent as real numbers, right? And that's assumed here from the outset. Here I'm assuming, of course, that a and b are real numbers, okay? I mean, some of these things would still be true if a and b were like infinite. If you multiply the product of infinite sequence is still infinite. There's some things that would transfer over to infinity, but let's focus on the convergent case here. And I've maintained the numbering from Salas and Hilly as well. If b is non-zero, then the quotient sequence converges in the natural way. If you have a constant sequence, I'll actually prove this one. If you have a sub n is just a constant c for all n, then this constant sequence converges to that constant. In other words, the very unsurprising limit as n goes to infinity of c is equal to c. Property 6 is super nice for some examples. I'll put an example up here in just a second to illustrate what that is. If f is continuous at a, then the limit of f of an is equal to that. So let's see here. For example, then equals to, say, sine of n over n. Of course, we can argue minus 1 over n less than sine of n over n less than 1 over n, right? Using the fact that sine is between minus 1 and 1 and dividing by n, right? So then, of course, this goes to 0, that goes to 0. Therefore, the limit as n goes to infinity of sine n over n by the squeeze theorem is equal to 0. Okay, great. So then here's the application. If I had f of x is equal to like tangent, right? Tangent of x, for example, then this is continuous at x equals to 0, right? And we could argue that f of sine n over n goes to, f of 0 equals to tangent of 0 equals to 0. All right? That'd actually be kind of a non-trivial application here. In other words, the limit as n goes to infinity of the tangent of the sine of n over n is equal to the tangent of the limit as n goes to infinity of sine n over n. I can pull that limit inside because the tangent's continuous. Of course, I just explained to you that that's at 0, so we get tangent of 0 which is equal to 0. So these, composing continuous functions and known limits, it's a very powerful technique. There are some good examples given 11.3. So I think I've saved it. Let me go on here. There are, oh man, this is my cover sheet. So there's 6. 7 is a list of kind of equivalent ways of looking. We says a sub n goes to L. That's if and only if. In other words, it's interchangeable with a sub n minus L going to 0, and that's interchangeable with the absolute value of a sub n minus L going to 0. So that's sometimes useful to think about. We'll probably come back to that at some point. We'll probably find ourselves needing to use that at some point, is what I'm trying to say. I just used 8, which is the squeeze theorem. All right. 9. Now this is new notation. That n much. So this to me reads n is much greater than 1. All right. So sometimes the textbook will say something like for n sufficiently large. So this would be another way of saying that if n is big enough. All right, if n is big enough, and suppose we have this inequality that the absolute value of Bn is less than Cn for n big enough, and suppose that Cn goes to 0. Well, guess what? Then B sub n must also go to 0. So that's a sometimes useful theorem. Now here's one immediate application of these limit properties. One application would just be to prove the uniqueness of the limit. All right, so here's a proof that I saw once upon a time. Suppose you have an goes to a, and an goes to a prime as n goes to infinity. All right. Then if you look at the limit of the difference of an and an, you get the difference of the limits, which you could say is a minus a prime. All right. But on the other hand, an minus an is just 0, and we know the limit of the constant sequence 0 is 0. So that shows me that a minus a prime is 0, which is to say a is equal to a prime. In other words, the properties 1, 2, and 4 force uniqueness of the limit. Now, if you don't think my argument's convincing, you can see the argument for theorem 11.3.2, which is given at the end of section 11.3 in Salas and Hilly. I should mention the proof of 3 and 4 are, I would not say that they're that easy, but they are given, and I think the proofs can be followed if you're a little bit courageous at the end of section 11.3. I will not take class time for those, but we'll be willing to use 3 and 4. We don't have quite enough airtime here to prove them. Maybe in a different semester I might prove them. I'm not saying it's outside the realm of possibility. It's just I have taken too much time on other things to have time to do them this semester, unfortunately. Now, here's some select proofs, though. All right, so one of the things I'll prove is 1. And here's how it goes. Suppose an goes to a, suppose bn goes to b, as n goes to infinity, all right? That means we can choose na, and we can, such that whenever n is larger than na, we can make an minus a less than epsilon over 2. All right, so to be fussy here, I should really at the start of this say, let epsilon be greater than 0, period. I should start with that. All right, so I fixed an epsilon greater than 0. For that epsilon greater than 0, I can choose na to make the distance between a sub n and a be less than epsilon over 2. And by the same token, I can pick an nb such that whenever n is larger than nb, I'm within epsilon 2 units from b. All right, I can do that because I'm assuming that an and bn both converge to a and b respectively. Okay, so as I said, let epsilon be greater than 0. Select na and nb as above. Okay, let n be the max of na and nb, and suppose that little n is larger than that max, right? And so that would mean that little n is greater than na, and little n is greater than nb, right? So we have both of those conditions, which means we get both of these conditions, which is great. And so if I look at the difference of an plus bn and a plus b, I just reorder the terms like so, right? That's just algebra. Then this step right here going from here to here is what's called the triangle inequality. This is something that's true for absolute values. Triangle inequality. And of course that's a great step to make, because then this is less than epsilon over 2, that's less than epsilon over 2, so we get that that's less than epsilon. So what we've just shown is that whenever n is larger, little n is larger than this n, that implies that the difference of the sequence and the alleged limit is less than epsilon, which is all we need to do to prove that an plus bn goes to a plus b by the definition of the sequential limit. All right? I don't know how much attention you've been paying to your homework or not, but this is the solution to one of your homework problems. So there you go. I hope, well, anyway, I hope this helps you understand. Now, you may recall proofs of limit proofs from Calculus 1, where we proved the limit laws with epsilon deltas. Very similar, but there we were controlling delta, here we're controlling n. Epsilon be greater than 0, suppose alpha is not 0. I'll let you think about it. If alpha was equal to 0, there's a separate and easier argument here. But we're going to suppose alpha is not 0 and an goes to a. I can select n sub a such that a sub n minus a is less than epsilon over the absolute value of alpha when n is larger than a. And if I consider n being larger than a, then we have this difference, factor out the alpha, pull out absolute value of alpha, but this is less than by construction of big N, epsilon over absolute value of alpha. These cancel, leave me epsilon, and therefore I have proved that the limit as n goes to infinity of alpha a to the n is equal to alpha a by the definition limit. This is, yes, again, part of your homework. So sorry to do some of your homework for you. Hope you'll forgive me. But, you know, you still do kind of need to process it, don't you? Now, the proof of 5 is even sillier. And so here 5, let epsilon be greater than 0, choose n equals to 42. I mean, why not? Answer to everything, right? Let's see here. Then for n greater than 42, we have that, I mean, this is stupid. I mean, honestly, what we need to show, which is that the difference between the sequence and the alleged, I mean, this right here is playing the role of an minus L, all right? Here L is equal to C and an is equal to C. So in this rather silly case, it's automatically true that that's equal to 0, which of course is less than epsilon because, you know, epsilon's positive. So proving that the limit of a constant sequence is the constant is just silly. I mean, there it is. The proof is there. And here's part of the proof of 7. If an goes to L as n goes to infinity, then the limit of a sub n minus L is equal to the limit of a sub n minus the limit of L. But we just proved the limit of a constant is the constant. And the limit of a sub n was given to be L, so you get L minus L, which is 0. So this going to that implies that the difference goes to 0. So, all right, well, there's part of it. You can, the textbook has more of it. I'm going to move on. So one of the other theorems we have, which is worth noting, and it's not hard to prove, it's a nice little proof. Every convergent sequence is bounded. Okay, so how do you prove that? Assume that an goes to L as n goes to infinity, all right, and then let epsilon be 1. I mean, we can do that. If it has to, we're able to make a sub n within epsilon units for any epsilon, so certainly we can do it for 1. And there has to be some k, such that whenever n is greater than or equal to k, k is playing the role that big N did in previous proofs here. And so whenever n is greater than or equal to k, that implies that the distance between an and L is less than epsilon, which is 1. So I can unwrap that inequality, minus 1 less than an minus L less than 1. Great. Add L, so I've got L minus 1 less than an less than L plus 1. And that's true for n greater than or equal to k, right? So certainly L minus 1 and L plus 1 serve as lower and upper bounds for an up there. And so if you want to bound for everything, well, just throw in everything before then. I mean, A1, A2, AK. I guess I don't need the k since that's also included here, but whatever, it doesn't hurt. Certainly the max of all these is going to satisfy that the absolute value of an is less than or equal to m. This gives me something that's larger than all possible terms in the sequence, which proves, of course, that that convergent sequence is bounded. Great. Now, this theorem I stated in last class, but let's talk about it a little bit more. This is the bounded monotonic sequence theorem, which says that an increasing sequence which is bounded above converges to the least upper bound. A decreasing sequence which is bounded below converges to the greatest lower bound. All right? And the proof actually is a simple adaptation of what we proved in class last time. So we'll just prove the increasing case. Suppose an is increasing and bounded above. Let L be the least upper bound, so that means an is less than or equal to L for all n. As we proved last class, if epsilon is greater than 0, then there is some k between L minus epsilon. Let's see, there's some k which is larger than L minus epsilon, right? And that means, of course, that's in S. I mean, S here is just the range of the sequence, all right? But the sequence was increasing, right? So that means that a sub k is less than or equal to an for all n greater than or equal to k. Thus, L minus epsilon less than, well, this is less than an, right? If there's an a sub k in between there. But, oh, by the way, an is less than or equal to L. We already have that, so we have this. And that implies that the absolute value of an minus L is less than epsilon for n greater than or equal to k, which is precisely what we need to prove that the limit as a sub n as n goes to infinity is equal to L. So there's the proof of the bounded monotonic sequence theorem. It's almost a corollary to what we did last class. There are many examples in section 11.3 which are all very nice. 9, 8, 11, 12, 13. I'm not even, just please read them. I don't even want to do them here. I'm going to spend my time on the thing which I think is more likely to confuse you. Not to confuse you, but because you need to see more examples because it's weirder, all right? So here's number 64. We're asked, here's a recursively defined sequence. Does it converge? Does it diverge? If it does converge, calculate the limit, all right? So here's the recursive definition. A1 is 1, a sub n plus 1 is n over n plus 1 times an. Great. Now, so here I started calculating. So I got a1 is 1, a2 is 1/2 a1, so that's 1/2. a3 is, well, 2 over 3 times a2, but a2 is 1/2, so, oh, the 2's cancel, I get a third. At this point I was like, oh, well, this is easy. I don't need the bounded monotonic sequence theorem to do this one. I can see that the formula for this thing is an, is 1 over n. And so that goes to 0 as n goes to infinity. And if you doubt that this is the formula for an, you could, of course, use mathematical induction to prove that. All right, that would be a good exercise if you want to test yourself on whether or not you understood that induction thing I was talking about a second ago. So there's a kind of, sort of a, I wouldn't say disappointing, but kind of not that hard of an example. Here's another one, 61. an plus 1 is 1 over e times an, and we're given that a1 is 1. So I decided to divide an plus 1 by an. That gave me 1 over e, which is less than 1, right? So that shows me that an plus 1 is less than an, which is to say that the sequence is decreasing, right? It's getting smaller as we go on. And therefore, by the bounded monotonic sequence theorem, the greatest lower bound of the range of the sequence, which, by the way, is pretty clearly 0, right? That's the limit of the sequence. The limit as n goes to infinity of an is equal to 0 by the bounded monotonic sequence theorem. But I will admit, for number 61, much like number 64, you could pretty clearly see the formula is 1 over e to the n minus 1, and you can see that that goes to 0 by the usual limit laws and, well, common sense. Okay, so just to recap, I have been proving some things, right? So when I expect an argument at the level of proof, I will say something in the problem statement along the lines of prove using epsilon n or something like that, okay? If, on the other hand, I just want you to calculate from limit laws, then I will just say, you know, find the limits or something where I hopefully am clear that I don't have as high an expectation of rigor or proof, okay? Because we do live in both both worlds, so to speak. Like these problems determine the boundedness and monotonicity of the sequence. Well, you got to follow instructions, right? So each one of these, you got to. I mean, if I'm not suggesting you work each one of them, but if you were, you'd be trying to figure out, is it increasing? Is it decreasing? Maybe it's neither. Is it bounded? Is it not bounded? I don't know. I mean, I can tell you number 31 just looking at it. That's bounded between -1 and 1. And goodness, as n goes to infinity, that's going to sine of 0. So if I had to wager, yeah, I don't think that actually is. It's gonna like, oscillate, and yet I believe that limits to 0, sine of 0. This would be a good one to feed into the composition of continuous function and convergent limit theorem. Cosine n pi, that's just -1 to the n. Anyway, let me stop talking about those. So that was, those are good problems to sort of cut your teeth on whether or not you understand boundedness. And goodness, the problems in 11.3, these are great problems, and I gave you guys the answers so we can kind of work through some of those. I mean, I can just tell you what happens. 2 to the n goes to infinity. -1 to the n over n, well, that goes to 0. You could use a squeeze theorem if you wanted, or you could use the absolute value of this goes to 0, therefore the sequence goes to 0. This one by algebra is 1 over 1 minus 1 over n, which of course goes to 1, because 1 over n goes to 0, limit laws. This is 1 over n plus 1 over n squared. Both of those go to 0, so that goes to 0. This one I have to think about a bit. I don't know right off. I have to think about that one a little bit. But anyway, these are a great list of examples to kind of try to cut your teeth on if you need more practice. If you really had a full treatment of the limits at infinity with x last semester and you're still fresh on that, then this stuff should be just a piece of cake. But if you're not, then it's important to work enough examples until you're kind of bored with it, right? Okay, well, that's all I got to say about sequences here. There's of course more to say, and if you're a math major, I would encourage you to read that chapter, and I will try to repost the PDF because I misposted it to start with. I meant to post chapter 11, and I've got some part of chapter 10, which was not my intent. So I'll try to repost it, especially for you math majors, because there is great wisdom in this chapter. It's a really nice foundation to have for yourself going forward in terms of just what is the basic analysis of real numbers. But tomorrow, Thursday, hopefully there will be no snow. We'll have class, and we'll start working on what is a series. So anyway, thanks everybody. Bye.